In Chapter 9, we switch from conducting hypothesis tests and constructing confidence intervals for one sample to comparing two samples. We begin in Chapter 9 by comparing two proportions. Now that we are looking at two samples from two populations, it's important that we use correct notation to tell the difference between the two. We will use P1 to notate the population proportion for the first population. N1 is the size of the sample that came from population 1. X1 is the number of successes in this sample, and P1 hat is the sample proportion from this population. We calculate this by finding the quotient X1 divided by N1, and Q hat 1 is 1 minus P hat 1. The same can be said for the other population. P2 is the population proportion. N2 is the size of the sample taken from this population. X2 is the number of successes in this sample, and P hat 2 is the sample proportion for this second sample, which we calculate using X2 divided by N2, and Q hat 2 is 1 minus P hat 2. We also have something called a pooled sample proportion. If we assume that P1 equals P2, that is, the two population proportions are equal to one another, or their difference is 0, that will be our null hypothesis. And then our P1 hat and P2 hat can be combined to provide the best point estimate of the common value of P hat 1 and P hat 2. The combined common value is called the pooled sample proportion. When we calculate a proportion, we have X over N. And if we want to combine our two samples, we'll have a total number of successes, X1 plus X2, and we'll have a total sample size of N1 plus N2. That's our pooled sample proportion. We use P bar to notate this, and necessarily then Q bar is equal to 1 minus P bar. There are some requirements as we head into this type of hypothesis test or this type of confidence interval. The sample proportions must be two simple random samples that are independent of one another. We also require that for each of the two samples, there are at least 5 successes and at least 5 failures. That is, for each sample, N times P hat must be greater than or equal to 5, and N times Q hat must be greater than or equal to 5. When we are conducting a hypothesis test for two proportions, our test statistic will be a z-statistic, and it is calculated like this. But notice that with our null hypothesis, we have P1 equal to P2. And with that assumption, it's also true that P1 minus P2 is equal to 0. That means that this difference in the numerator is equal to 0 when we have this as the null hypothesis. And that simplifies the formula. The numerator just has P1 hat minus P2 hat minus 0 divided by the square root of P bar times Q bar over N1 plus P bar times Q bar over N2. Thankfully, our calculator function will give us this z-statistic. The calculator function that we'll need here is 2-prop z-test. Now let's look at what we're going to need to construct a confidence interval for two proportions. A confidence interval estimate of P1 minus P2, that's the difference of the two population proportions, can be found by taking our best point estimate, P1 hat minus P2 hat, plus or minus the margin of error, E. In other words, we have P1 hat minus P2 hat minus E is less than P1 minus P2, and P1 hat minus P2 hat plus E is greater than P1 minus P2. That gives us an interval where we believe that the difference between the two population proportions is. The margin of error can be calculated this way. Our z sub alpha over 2 value is determined by the confidence level and our z distribution, and the rest is found by using our two sample proportions. The calculator function for constructing a confidence interval estimate of P1 minus P2 is 2-prop z int. This might feel like a lot of information to keep straight, but if you're asked to test a claim, do a hypothesis test. If you need to estimate the actual difference, then construct a confidence interval. Let's try out an example. A study was conducted to determine the proportion of people who dream in black and white instead of color. Among 306 people over the age of 55, 68 dream in black and white, and among 298 people under the age of 25, 13 dream in black and white. It is claimed that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. Let's start by pulling out the information for the two samples. Let's define our first sample to be those over 55. Since we have a total of 306 people in the sample, we have that N1 is equal to 306. And since 68 dream in black and white, we have X1 is equal to 68. This gives us a sample proportion P1 hat of 68 divided by 306, or 0.2222. For our second sample, people under 25, we have a total sample size N2 equal to 298. And the number of successes, X2, is equal to 13. This gives us a sample proportion P2 hat of 13 divided by 298, or 0.0436. Now let's determine the claim. Since we have that the claim is that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25, we can express our claim as P1 is greater than P2. It's also requested that we use a significance level of 0.01. So that's our value for alpha. Now we have everything we need to conduct our hypothesis test. The first step is to determine the null and alternative hypotheses. The null hypothesis is the statement of equality that the two proportions are equal to one another. That is, there's no significant difference between the two population proportions. The alternative hypothesis in this case will line up with our claim that P1 is in fact greater than P2. The second step is to calculate the test statistic. We can do this by hand by using the formula for the test statistic. Or we can use the calculator function 2PROP-z-test. Let's try out that calculator function. This function is found by going to Stat, toggling over to Tests, and scrolling down to 2PROP-z-test. Now we can enter the values from our samples. For X1, we had 68, and N1, 306. Our X2 was 13, and N2, 298. We also want to select greater than P2. That represents the alternative hypothesis that P1 is greater than P2. Using the down arrow, we can highlight Calculate and press Enter. This gives us our test statistic Z equal to 6.44. Notice that this screen also gives us our p-value of 6.01 times 10 to the negative 11th. Let's take this information back to the example. We found a test statistic, Z equals 6.44. The third step of our hypothesis test is to calculate the p-value or critical value. The easiest thing to do in this situation is use the p-value given to us by the calculator function. We found a p-value of 6.01 times 10 to the negative 11th. If you want to instead go the critical value route, you would need to find the z-score that has a left area of 0.99, and that would give you a value for z equal to 2.33. Let's use this information to draw a picture. The center of this curve is the null hypothesis that P1 is equal to P2. That also corresponds to a z-score of 0. We found a critical value of 2.33. And that corresponds to our alpha or significance level of 0.01. We also have a test statistic of 6.44, which is way farther to the right, which corresponds to a p-value or right area of 6.01 times 10 to the negative 11th. Rounding that to 4 decimal places, we get 0, and we can notate that with a 0 plus. That simply means that the value isn't 0, but it is so small that it rounds to 0. That brings us to the final step of our hypothesis test, stating the conclusion. Using the p-value method, we find that the p-value is less than alpha. And using the critical value method, we find that our test statistic z is in the critical region or rejection region. Either way, we reject the null. That is, we reject the null hypothesis that P1 is equal to P2, which gives us some evidence to support the claim that P1 is greater than P2. We might state our conclusion by writing a full sentence like this. There is sufficient evidence to support the claim that the proportion of those over 55 dream in black and white more than those under 25. That is, there's evidence to support the idea that P1 is greater than P2. Now let's look at this same example through a slightly different lens. In part B of this example, we're going to instead construct an appropriate confidence interval to estimate the difference between the two population proportions. When we say appropriate confidence interval, that means we want it to correspond to the hypothesis test that we just conducted in part A. We want to choose the right confidence level so that the two tests match up. In part A, we had a right-tailed hypothesis test with the area in the right tail equal to 0.01. That was our value for alpha. In order to have a corresponding confidence interval, we need to mirror that right tail over to the left and have another tail with area 0.01. That leaves 0.98 left for the center, or a 98% confidence level. That means that the corresponding confidence interval estimate in this case would have a confidence level of 98%, or 0.98. Let's again use our calculators and this time construct an interval. The function that we're going to need on our calculator is 2prop z int for 2 proportion z interval. We can find this function in the stat menu by toggling over to tests and scrolling all the way down to option B, and we can press enter while B is highlighted. Notice that our sample information is already entered as x1, n1, x2, and n2. Our calculators will bring that information over from the 2prop z test. What we do need to adjust is the confidence level. We want a confidence level of 98%, or 0.98. And now we want to press enter while calculate is highlighted. This gives us our confidence interval from 0.117 to 0.240. Let's take this back to the example. We have a 98% confidence interval estimate for the difference between the two proportions of 0.117 to 0.240. Another way to write this would be that we believe that the difference between P1 and P2 is between 0.117 and 0.240. Let's think about what this implies about the difference between these two proportions. First of all, notice that this interval does not contain 0. The fact that it doesn't contain 0 implies that there is a significant difference between the two population proportions. If 0 was in this proportion, then that would mean that it's possible that P1 minus P2 is equal to 0, or that P1 is equal to P2. But since 0 is not in this interval, that implies that that's not true. We are 98% confident that P1 is not equal to P2. There is a significant difference between the two population proportions. At least that's what's implied by this sample data. Also notice that all of the values inside the interval are positive numbers. Having them all be positive implies that P1 minus P2 is greater than 0. And adding P2 to the other side, we have that P1 is greater than P2. So this confirms the same result that we found with our hypothesis test, that P1 is greater than P2. Now let's take a look at a second example. A study investigated survival rates for in-hospital patients who suffered cardiac arrest. Among 58,593 patients who had cardiac arrest during the day, 11,604 survived and were discharged. Among 28,155 patients who suffered cardiac arrest at night, 4,139 survived and were discharged. We want to use a 0.01 significance level to test the claim that the survival rates are the same for day and night. We'll start this example the same way we started the last example, by listing out the information given for the two samples. We'll have our first sample consists of those patients that suffered cardiac arrest during the day. The total sample size, or N1, is 58,593, and the number of successes in this case, X1, is 11,604. Those are the patients that survived. This gives us a sample proportion, P1 hat, of 11,604 divided by 58,593 of 0.1980, or just under 20%. Now let's look at the other sample. The second sample will consist of those patients that suffered cardiac arrest during the night. The sample size here, N2, is equal to 28,155, and the number of successes, X2, is equal to 4,139. This gives us a sample proportion, P2 hat, equal to 4,139 divided by 28,155, or 0.1470, just under 15%. Consider what's being claimed. The claim is that the survival rates are the same during the day and night, and we can express that claim as P1 is equal to P2, that there is not a significant difference between the two population proportions. We are also asked to use a significance level of 0.01, so that's our value for alpha. Now that we have all of this information recorded, let's conduct our hypothesis test. The first step is to determine the null and alternative hypotheses. The null hypothesis is the statement of equality that P1 is equal to P2. That's the idea that there's no significant difference between the two proportions. Notice at this time, the null hypothesis lines up with our claim. So the alternative hypothesis will be the statement that they are not equal, that P1 is not equal to P2. This also tells us that we have a two-tailed test to conduct. The second step is to calculate the test statistic. We can use the formula or the calculator function. I prefer the calculator. We'll get to our calculator function by going to Stat, Tests, and scrolling down to option 6, 2-prop z-test. This time X1 is 11,604 and N1 is 58,593. X2 is 4,139 and N2 is 28,155. We have a two-tailed test, so we want to select not equals P2. This represents the alternative hypothesis as P1 is not equal to P2. And scrolling down to calculate, we can press enter to run the hypothesis test. This gives us our test statistic, z equal to 18.26. It also gives us our p-value of 1.8 times 10 to the negative 74th. Let's take this information back to the example. Using our calculator, we found the test statistic to be z equal to 18.26. We also found the p-value, which we need in step 3. We found the p-value to be 1.8 times 10 to the negative 74th power. And if you instead wanted to use the critical value method, you would have the two critical values for the two-tailed test of 2.58 and negative 2.58. Let's go ahead and put this on a picture. Again, our normal curve is centered on the idea that P1 is equal to P2. That's our null hypothesis, and it corresponds to a z-score of 0. We have a two-tailed test with alpha equal to 0.01. Splitting that into the two tails, we have alpha over 2, or 0.005, in each of the tails. I'll go ahead and add the critical values of negative 2.58 and positive 2.58 to our picture, since we have them. But our test statistic is 18.26. That is so far off to the right, it's more than 18 standard deviations away from the center. And it corresponds to a p-value, or an area to the right, of 1.8 times 10 to the negative 74th. That would be 73 zeros after the decimal place, before the 1 and the 8. So we'll again express this as 0 plus, to notate that it is a positive number, but it rounds to 0. This brings us to our conclusion, step 4 of the hypothesis test. The p-value is clearly smaller than alpha in this case, and the test statistic is clearly in the rejection region. So we will again reject the null. We could state our conclusion by writing something like this. There is sufficient evidence to reject the claim that survival rates are the same during the day and night. Now let's go on to part B, and again we'll construct an appropriate confidence interval estimate that corresponds to this hypothesis test. With a significance level of 0.01 split into the two tails, our hypothesis test already has the two tails we would need for a confidence interval estimate. So we don't need to mirror image anything. So from this information, we find that in the center, we have 99% or 0.99 left over, and that will be our confidence level. Using our calculators to construct this confidence interval estimate, we need to use the function CHOOPROP-ZINT. This time we'll go to Stat, Tests, and scroll all the way down to option B for 2PROP-ZINT. Notice that once again, our values for x1, n1, x2, and n2 came over from our 2PROP-Z test. What we do need to do is adjust our confidence level. This time we have a 99% confidence level, and so we need to enter 0.99. When Calculate is highlighted, we press Enter. This gives us a confidence interval of 0.044 to 0.058. And we can take that back to the example. We are 99% confident that the interval from 0.044 to 0.058 contains the actual difference between the two population proportions. In other words, we believe that P1 minus P2 is between 0.044 and 0.058. Let's think about what this implies. We again do not have 0 inside this interval. That implies a significant difference between the two population proportions. We also notice that the values are all positive, and having the difference between P1 and P2 being a positive number, that implies that P1 is greater than P2. That implies that the survival rates are greater during the day than during the night. Now we have both a hypothesis test and a confidence interval estimate to confirm the same information about these two samples and what they imply about the two populations. That concludes this lecture video on running a hypothesis test and constructing a confidence interval estimate for two proportions.